So last class we have discussed about the IV infusion up to the your equation, that is first equation, that is the third and fourth equation you got, that is after IV infusion we can say the drug administered, so you can say it is C is equal to R0 by CLT, or C is equal to R0 by KE into VD into 1 minus e raised to minus K into T. That is the third equation. We know that Ke into Vd is total clearance, so it is given as CLT. Then we have explained that at the start of infusion the drug concentration will be 0 and the time passes, the amount of drug present in the body increases until it rate of elimination equals to the rate in, that is rate of absorption. That is at steady state we have rate in is equal to rate out. Then we have derived an equation, and also the graph is plotted when we have explained the equation also. So in that we have explained that to steady state rate of infusion is equal to rate of elimination. So finally after derivation we got CSS is equal to R0 by K into Vd, or CSS is equal to R0 by CLT. That is the equation, sixth equation. So you got the equation for steady state and equation for after IV infusion. We got two equations. Okay. Then next step will be the determination of parameters. First one is the elimination rate constant. So the elimination rate constant can be obtained by two methods, and the simple method is the semi-log plot of elimination phase from time when infusion is stopped. That is, when the concentration of the drug in the plasma, you can plot a graph, that is concentration of the drug in the plasma versus time. You will get a graph, the normal graph. The rate of infusion increases and reaches the steady state, and when infusion is stopped you will get only the elimination phase. So you can take this elimination part and plot it on another graph, that is log C versus T of the elimination part. So you will get a straight line. Take the slope of this. The slope is equal to Ke by 2.303, and the half-life is equal to 0.693 divided by Ke. That is the first method. So if you have to plot two graphs, from that the elimination phase you have to take the log concentration versus time. You will get a straight line, take the slope and find out your K. That is a simple method. Then the another alternative method. So on the first one we have taken the data from the elimination phase. On the second method you can take data from the start of infusion to the steady state. This part, this data will be taking. So and we know that from the earlier equation CSS is equal to R0 by CLT. CSS is equal to R0 by CLT. That's a steady state concentration equation that we have already derived. Then that we will be applying in the your third equation. There C is equal to R0 by CLT into 1 minus e raised to minus K into T. There we will be substituting this CSS. Instead of R0 by CLT we will be substituting CSS. Okay. So in substituting that in equation 3 we will get C is equal to CSS into 1 minus e raised to minus Ke into T. Then we will be going for some rearrangement. Rearrangement means we want to bring all the concentration term on the one side, to the left hand side. So first simplification, then the rearrangement, these two steps. So you will get CSS minus C divided by CSS is equal to e raised to minus Ke into T. Then you can convert this into its log form. It's a log form. So it is log CSS minus C divided by CSS is equal to minus Ke into T divided by 2.303. This is the log equation what we got. Okay. So you got a log equation, linear equation. So you can plot the graph. You will get a linear graph, that is log CSS minus C divided by CSS versus T. So you will get a straight line. Take the slope of the straight line. It will give you slope is equal to minus Ke divided by 2.303. So this is the alternative method. That is, you are collecting the data from start of infusion up to your steady state. Okay. By this we will be deriving an equation. Finally we are plotting log CSS minus C versus T. So you will get a straight line, take the slope and find out Ke. That is, slope is equal to minus Ke by 2.303. So that's the two methods to find out elimination rate constant. If you know the elimination rate constant, you can find out half-life. Okay. Next is the time to reach the steady state. We told you our ultimate aim is to maintain the steady state concentration in the blood plasma. Then when the steady state concentration is reached in the blood plasma, the time to reach the steady state depends on half-life, not the rate of infusion. If you increase the rate of infusion, the intensity of action may increase, but it won't affect the time to reach the steady state concentration. The time to reach the steady state concentration of the drug in the plasma always depends on the half-life of the drug. So if the drug is having less or short half-life, then it will take only lesser time or a shorter time to reach the steady state concentration. And if the drug is having higher half-life or longer half-life, means it will take long time to reach the steady state concentration. That's the problem. So in that case, how will you maintain the steady state concentration in the blood plasma? For that, we are using a therapeutic application that is called as the infusion plus loading dose. It's called as the infusion plus loading dose. Okay, if a drug is having a longer half-life, it is like more time to reach the steady state concentration. In that case, we will be using infusion plus loading dose. That means you will be administering the infusion immediately prior to the infusion. The drug is administered as IV injection. That is called as the loading dose. Drug is administered initially as a IV injection. That is called as the loading dose. Okay. Example of a drug is having high half-life is given. That is phenobarbital. Okay. Then immediately upon prior to the start of infusion, you have to give a loading dose. So this is the graphical representation of infusion plus loading dose. So this is the amount of the drug present versus T half. The amount of drug present versus T half. So this is the start of infusion and slowly increasing the concentration of drug. This is the start of loading dose, means it is administered as injection. So slowly the drug concentration decreases. This is representing both infusion plus loading dose. So that graph is also important. Then we have equations for IV infusion and also the equation for steady state. Next, we have to derive an equation for loading dose. We have administered drug as IV injection, so you have to find out the amount of drug administered after IV injection, that is loading dose. It is given by the equation that is dB is equal to VD into C. We are making use of this relationship. So after loading dose, we can write it as D0BL is equal to VD into CSS. Or we can say the steady state concentration of loading dose equation, we can write it as CSS is equal to D0BL divided by VD. CSS is equal to D0BL divided by VD. So it is differentiating as loading dose, we are writing as D0BL. D0BL, it is written as D0BL. That's the equation for loading dose, we can write it as. So we know that CSS is equal to R0 by Ke into VD or R0 by CLT. But we are taking this equation, the third equation. CSS is equal to R0 by Ke into VD equation we are taking. So that we will be substituting the above. In place of CSS, we will be writing R0 by Ke into VD. So you will get R0 by Ke into VD is equal to D0BL divided by VD. Okay, VD and VD get cancelled. That's why you have taken this equation instead of CLT for getting cancelling that VD. Okay, so finally you will get D0BL is equal to R0 by Ke or D0BL is equal to R0 by Ke. That's the equation for loading dose. So we have equation for infusion and loading dose. For the infusion, we will be taking the equation 6 and for the loading dose 12. Our aim was to maintain the steady state concentration by administering infusion plus loading dose. That means we have an equation for infusion 6 plus the loading dose. If you add these two, this should be equal to the steady state concentration. That is our aim. For that we have derived the equation. Next we have to prove that by adding equation 6 and equation 12, it is equal to the steady state concentration. Okay. So the C is equal to equation 6 R0 by CLT plus R0L divided by K. Both equations are almost same, but in differentiating we have given this L. This is for loading dose. Then we will be substituting for R0 with CSS into KE into VD and R0L with CSS into VD. CSS into VD for R0L, and for R0 we will be substituting CSS into KE into VD. Okay. So in this we will be directly substituting. We are not going to explain, or we are not going for showing the steps. In the simplification steps we are not showing it here. We are directly writing. After writing, you can say that CSS is equal to R0 by CLT plus R0 by L by KE, and you are substituting with this for R0 and this with CSS into VD for R0L. Then you can directly write it as, after after simplification you can directly write it as C is equal to CSS. So after substituting this and the simplification, we will get C is equal to CSS. That step we are not mentioning here. No need to write that. Directly you can write C is equal to CSS. That indicating the concentration of the blood in the plasma remains constant throughout the infusion time. This indicating that the concentration of the blood in the plasma remains constant throughout the infusion time. So that was our aim. If you administer drug as infusion plus loading dose, then the concentration of the drug in the plasma is equal to the steady state concentration. For that we have derived this. So under the determination of parameters of IV infusion, we have to determine KE by 2 method, direct method, that 2 graphs you have to show. Then by alternative method, that is up to CSS. So you will get log CSS minus C divided by CSS, that is versus T graph. From the graph you can again find out KE. Then next one, infusion plus loading dose, that also you have to write it down, and that graph you have to plot, and the equation, and finally you have to prove that C is equal to CSS. Okay.